Good afternoon. My name is Silvia Casarotto and I work at the University of Milan. Today I'm going to talk about how to collect and distinguish genuine EEG responses to TMS. TMS EEG is very useful to measure cortical excitability and effective connectivity. However, we have full freedom of choice when selecting TMS parameters. We have to decide where to stimulate, at which intensity, and with which 3D rotation of the coil. In addition, there are several factors that cannot be well controlled a priori and that can affect the impact of TMS on the cortex. These factors include neuronal excitability, axonal displacement, and mesoscale anatomy in the stimulated site. Thus, it is difficult to predict to what extent a certain combination of TMS parameters will actually activate cortical neurons. Nonetheless, we know that a direct and effective stimulation of cortical neurons should produce a local activation that spreads towards distant sites according to functional and anatomical connections. So, in principle, if we were able to monitor EEG data quality in real time, we could adjust TMS parameters to improve the signal-to-noise ratio. In other words, we could take advantage of the EEG readout to prevent the occurrence of clear-cut artifacts and to increase the impact of TMS on the cortex. This kind of approach is routinely applied, for example, during ultrasound investigation. Here, the operator empirically adjusts the location and orientation of the ultrasound beam to get a robust echo before evaluating a target organ. In the TMS field, this approach is also routinely applied, for example, when measuring peripheral motor evoked potentials. In this case, the operator coarsely places the coil over the primary motor cortex and then slightly adjusts the precise location and orientation of the coil and the stimulation intensity until the electromyographic activity recorded from a target muscle satisfies specific latency and amplitude requirements. Here, we propose to apply the same approach also when running TMS EEG experiments, because we think it's important to allow the operator to slightly adjust TMS parameters while relying on a real-time EEG readout. But what do we need to implement this approach? We need a dedicated graphical user interface that provides a customized display of TMS EEG data in real time. Our group has already developed such a software which is compatible with different EEG amplifiers. We will make the source code of this software freely available soon, but today I want to describe the basic features of this software tool and how they can help preventing the occurrence of clear-cut artifacts and can allow to appreciate the characteristics of genuine EEG responses to TMS. First, the software tools allows to inspect single trial EEG responses to TMS. This is very important because large artifacts with a distinctive time course can be easily detected on single trial data. So the operator can early adjust TMS parameters to prevent their occurrence. Secondly, the software tool allows to visually inspect average TMS evoked potentials. And this is also important because from a provisional average of, say, 20 trials only, the operator can already coarsely but reliably measure the signal-to-noise ratio of EEG responses and can also check for the possible occurrence of spurious components. These components usually are low in amplitude but time-locked to TMS, and thus may arise only after averaging a few trials. This is, for example, the case of auditory potentials evoked by the coil's click, which may appear when masking procedures are not properly applied during TMS EEG recordings. Now, what typically occurs when starting a new TMS EEG measurement session is that the operator sets stimulation parameters, so the stimulation target, orientation, and intensity, and then delivers a single pulse. And what does the operator can see on the EEG display in real time? Basically nothing, because of the pulse artifact, which spreads everywhere and is huge, 3 orders of magnitude larger than EEG activity. So there is no way to set the amplitude range of the signal in order to see both the artifact and EEG activity at the same time. This artifact is produced by the interaction between the strong and impulsive magnetic field produced by TMS and the EEG leads and amplifiers circuitry. Luckily, the duration of the pulse artifact exclusively depends on the electro shape and on the hardware characteristics of the EEG amplifier, such as measuring range, filtering bandwidth, and sampling rate. Once these hardware characteristics are known, the duration of the pulse artifact is also known. So in our software tool for real-time EEG data display, we simply mask the pulse artifact by replacing it with a flat signal. In this way, we can adjust the amplitude range in order to see EEG activity. But remember, this artifact is only apparently gone. It is still present in the raw data recorded. So, as a first pre-processing step, we have to remember to replace this artifact with a smooth fake signal before applying any further data processing procedures, such as filtering or whatever. Great, so let's restart our TMS EEG measurement session after masking the pulse artifact. We deliver a single pulse, and what do we see on the screen? We see another artifact. It is smaller than the pulse artifact, but still quite big as compared to EEG activity. It spread everywhere and has a weird waveform occurring in the first tens of milliseconds after the pulse. This is the recharge artifact. Where does it come from? Well, the stimulator's capacitors need to be recharged between subsequent pulses. In case there is a transient current flow or a change in the potential of the coil during the recharging, this artifact appears in the EEG, and its duration and waveform strongly depend on the stimulator's characteristics. Since the stimulator's capacitors typically recharge immediately after pulse delivery, the solution to get rid of this artifact is to delay via software the time of recharging beyond the temporal window of interest for TMS evoked potentials. Great, so let's restart. We have masked the pulse artifact and delayed the recharge artifact. Do we see the single trial EEG response to TMS? Well, here the signal is much improved as compared to the previous examples, but we still have an artifact. This artifact is not as big as the pulse artifact or the recharge artifact, but it is quite annoying for 2 reasons. First, it has a long duration. It lasts several tens of milliseconds after the pulse. And also, secondly, it occurs typically close to the stimulation site. It is the discharge artifact. This artifact is due to the fact that TMS pulses may charge the capacitances located along any possible induction current path, such as at the electrogel interface and at the gel-skin interface. Immediately after being charged by the pulse, these capacitances discharge and produce a decaying artifact. The solution to get rid of this artifact is to carefully prepare the skin for lowering its resistance and to use EEG electrodes with a shape that facilitates this skin preparation. Okay, now we can restart our measurement session. We have masked the pulse artifact, delayed the recharge artifact, and carefully prepared the skin. Do we see the single trial EEG response to TMS? Well, we still may see an artifact superimposed to EEG activity. This artifact can be quite big. It appears as a biphasic waveform followed by a slow return to baseline lasting several tens of milliseconds, and it is largest on the lateral aspects of the head. It is the muscle artifact. The muscle artifact is produced by either direct stimulation of muscle fibers by TMS or by the activation of the nerves innervating the muscles. Skull muscle twitches can be perceived by the examined subject, thus potentially producing unspecific brain responses to sensory stimulation. So the solution to get rid of this artifact is to maximally prevent its occurrence by adjusting stimulation parameters. And this task is not as difficult as it could seem at first sight. Let's zoom on the lateral aspects of the head where this artifact is largest. In this case, if we stimulate exactly the same cortical site at the same stimulation intensity, but slightly rotating the coil by 30 degrees, we can see that the muscle artifact has disappeared. In our experience, often a slight change in the coil orientation or a tiny shift in the coil position are enough to successfully prevent muscle artifacts without significantly changing the overall TMS parameters. Great! Now we have a single trial EEG response to TMS, which is devoid of large visible artifacts. So we can start averaging, say, the first 20 trials to visually inspect average TMS-evoked potentials, TEPs. First of all, when we say potentials, we actually mean potential differences between each channel and a common physical reference site. So, skull potentials are always affected by the location of the physical reference because in our body there are no neutral reference sites. This is clear if we look at the TEPs in common reference recorded over different channels. Their waveforms are very much correlated, and this is an effect of a common physical reference. To reduce this effect, it's possible to re-reference each channel to a linear combination of the recordings from all channels. This solution is called average reference. But we have to remember to exclude from the computation of average reference bad channels such as this one, because if we include this bad channel in the computation of the average reference, the result is that this artifact is spread everywhere. Similarly, we have to exclude from the computation of average reference also flat channels, because after re-referencing, these channels do not appear as flat anymore, but this is clearly an artifact. So the real solution is that we have to look at TEPs in average reference computed over good channels only. In this way, we can see that the largest response is evoked close to the stimulated site and early after the pulse as compared to longer latencies. In addition, we can see that there is a left-right asymmetry in amplitude of TEPs, which is in line with the stimulation side. If we apply this procedure when running TMS-EEG experiments, we immediately see that if we change the cortical stimulation site, for example, we stimulate the left premotor and the left parietal cortex at the same stimulation intensity, we should obtain different EEG responses, with the largest responses that follow the stimulation target. Similarly, if we stimulate exactly the same cortical target at a different intensity, we should see larger responses after stronger stimulation and smaller responses after weaker stimulation. Again, if we stimulate the same cortical site at the same stimulation intensity but with a different coil orientation, we should see different EEG responses to TMS. And all these results have been visually obtained by looking at 20 trials average. And as I can show you in this example, already after the average of the first 20 trials, you can have a quite reliable measurement of the amplitude of the early EEG responses to TMS, which is very similar to what you can obtain after averaging 100 trials. So to conclude, what is the take-home message of this rather educational and I hope not too boring talk? First, artifacts and spurious components have a weird or stereotypical waveform. Conversely, genuine TMS-evoked EEG responses are site-specific as well as intensity and orientation dependent. This means that EEG responses to TMS, genuine EEG responses to TMS, are highly sensitive to stimulation parameters. And this sensitivity, this specificity, is evident not only right after the pulse, but also at longer latencies and lasts several hundreds of milliseconds. Thank you for your attention.